Okay, so first things first, let's take a quick look at some important vocabulary. There's not much. The vocab assignment that you get in 3-4, it really only covers 3 or 4 things, and it's just this. If I asked you to write an absolute value function in vertex form, you would tell me, well, it's a function, right? So f of x equals what? Equals what?
A
times
H
absolute value of x minus h.
J.
That's it, right? Remember, the h is what's being subtracted from x inside the parent function, whatever it is. In this case, it's absolute value. A is what we're multiplying out front by the function. K is what we're adding outside of the function. And the reason we call this vertex form is because the vertex has coordinates what? HK. There you go. Piece of cake. So that's one thing you need to know. What if I do a quadratic function in vertex form? It's the same dang thing, isn't it? What's the only difference?
It's quadratic.
It's quadratic instead of absolute value. So the function, instead of being absolute value bars, it's a quantity squared, right? So this just looks like f of x equals, instead of absolute value bars, I get this quantity that's being squared. So I just get a times the quantity x minus h squared plus k, right? It's in vertex form. Well, what's the vertex? Same thing, hk, right? And then a is always just the vertical dilation factor, telling us what we're multiplying the parent graph heights by to either stretch them or compress them. If it's negative, it actually reflects them then too, right? Okay, how about a quadratic function in standard form? F of x equals what? Ax squared plus what? Plus bx plus c. Exactly, right? And that's kind of our simplified form. Whenever you just collect all the like terms and use, and simplify using order of operations, you always end up in standard form, right? And this one's a little tougher to deal with, right? This one, in order to find the coordinates of the vertex, we had a little formula that went with that. What's the x coordinate of the vertex? X equals negative b over 2a, right? That's telling us the equation of the line of symmetry. At the same time, it's telling us the x coordinate of the vertex. And then the very last one is one that we're not even going to use this unit, but we're going to use it in unit 4. And now's a good time for you to remember it. And you'll see why in a second. Now, instead of a quadratic function, what if we do a quadratic equation in quadratic equation in standard form? Okay, here's the deal. All that means is it's going to be a standard form quadratic function set equal to 0. That's it. So it just looks like ax squared plus bx plus c equals 0. That's it. Okay, that's a quadratic equation in standard form. And we'll talk a lot more about that next unit. Not so much this unit. All right, so now let's get down to business here. Let's graph. All we're going to do today is we're going to graph a quadratic function in standard form and a quadratic function in vertex form. And if you can do those things, you're in pretty good shape, because everything else is really just associated with that process, everything else we've talked about. Okay, so if we're going to solve we're going to graph a quadratic function in standard form, that's the harder of the two things to do. Graphing a quadratic function in vertex form is pretty easy, because you can just see where the vertex is, right? And then all we're gonna do from the vertex is just stretch or compress the parent graph shape. That's it, right? So that's pretty easy. This is a little tougher. There's a few more steps involved. This is the one where we can't just immediately see the vertex. We've got to calculate it. And this is one where it's easier for us to just use a t-table to get some key points that will graph to give us the shape of the parabola. Okay? So we want to focus on the vertex, right? That's the most important row. How do I find the vertex? You guys already told me the formula. What was that again? Negative b over 2a. Okay, so if we want to find the x-coordinate of the vertex, it's negative b over 2a, and if I plug values in, well, what are my values of a, b, and c? A equals, b equals 32, everybody. C equals, that wasn't everybody. So if I want to plug those numbers in, right, I'm just going to plug in negative b. If b is 32, what's negative b? Okay, divided by 2 times 4. Good. So negative 32 over positive 8, what's that? Good. Negative 4, good. So then our axis of symmetry is x equals negative 4. Okay? So we'll draw that one in. Negative 4 is right here. And so there's our axis of symmetry. We know that the vertex has to be on that line, right? So then how would I find the coordinates of the vertex? We know the x-coordinate is negative 4. How would I find the y-coordinate? Plug it in, right? How do I ever find a y-coordinate if I have a function? I plug in the x value, right? Okay, so let's down here will be where we'll maybe plug in some values. So if I want to plug in negative 4, what's our rule when we're evaluating a function? Every place I have an x, I'm just going to open up an empty quantity for dumping a value in. So I get 4 times something squared plus 32 times something plus 66. And the value we're plugging in is negative 4. So what's that going to give us? What's negative 4 squared? Times 4. I heard it. 64. Plus 32 times negative 4. Well, that's going to be negative. Just double 32 twice. When you multiply by 4, you double it twice. So 32 and 32 is 64. Double 64, I get. Okay. Plus 66. Let's combine the positive. 64 and 66 is 130. 130 minus 128. What's 130 minus 128? 2. Ooh. Okay, so then we get the point negative 4, positive 2. So there's our vertex, right? Okay. So now what? We found the vertex. Now what? Plug in a point. Plug in a point. It's going to be plug in a point. What x value would be convenient to plug in here? We want to pick one close to our vertex, close to the axis of symmetry, which is at negative 4. So negative 3 would be a good one, wouldn't it? We could pick negative 3 or negative 5, but we want to pick the smaller number to plug in, right? So we'll pick negative 3. And if I plug negative 3 in, what are we going to get? Well, let's find out. So here's so if we plug in negative 3, what's that going to give us? Negative 3 squared is 9 times 4. 36, good. 32 times negative 3, negative 96, plus 66. So what do we get? 36 and 66 is 102, right? 102 minus 96 is 6, okay? So we get the point negative 3, 6. So there's negative 3, positive 6. Okay, and then I could just reflect that point over the axis of symmetry to get the point on the other side of the axis, right? Because we know that the parabola has that line or that folding symmetry. And then all I have to do is just connect and extend. Right? There's our parabola. So that's a perfectly legitimate way to do it. Now, I want you to notice something here. See if somebody can explain this to me. If I go over 1 to the right, can somebody tell me why is it that we're going up by 4?
Because 4x squared.
There you go. Because a is equal to 4, right? That's it. Now how come? If a is equal to 4, that's the vertical dilation factor is 4. Think what that is. There's another way to do this one, right? We could use the t-table, and that's fine. But we could have even maybe sidestepped that a little bit. Once we know where the vertex is, a is what tells us what we're going to multiply all of the normal heights by, right? Now, if I were to draw a regular old parent graph, let's take just a second and do this. Okay, so if I'm drawing a regular parent graph for x squared, what does it look like? Normally I would start at the origin. If I go 1 to the right, I go up how far? I go up 1 squared, which is 1, right? So I go up by 1. If I go 2 to the right, I go up 2 squared, which is 4, right? If I go 3 to the right, I go up 3 squared, which is 9. And that's why the parabola bends upward, right? Because the y values keep increasing. As I square them, the numbers get really big pretty fast. And that's what bends it up, right? So it's a u instead of a v. So if I go to this page over here then and I think, okay, well, normally if I go to the right by 1, I would go up by 1. What do I do to the normal parent graph values? I multiply by a, right? 1 times a, which is 4, is equal to 4. That's why I'm going up by 4. I'm going up my normal parent value times a. Okay, everybody see that? Right. You distracted me. He's having a hard time, so just please focus. No, it was good. It was good.
Very good one.
It was good. Rodney knows what he's done.
Yeah.
He's on gear, he's on gear.
Okay, right? Everybody see that?
Yeah.
So which way do you use? I mean, take your pick. You can use the t-table. That's kind of tried and true. But if you can think about it this way, if you can think about it in terms of just stretching a parent graph, it's easier to do. It really is. Okay, in the long run, it's going to be easier for you to think about it that way. Okay. So what about questions on that? That make sense? On Moodle, what are you looking for? You're looking for that graph. How do you know it's that graph? Because it's the graph that goes through those points, right? Those are the points that you'll look for, the one parabola that goes through those points. Only one of them could. It's the right one. Okay. All right, what about this one? This is much easier. This is in vertex form, isn't it? Right? This is in the form f of x equals what?
A times x minus h plus k.
H squared
Yeah.
plus k. So then what are the values of a, h, and k?
1/3.
So our vertex, we already know, is at what? -1, -2. There you go. Already done. So the vertex is at -1, -2. If we had to write down our axis of symmetry this time, if it's in vertex form, the axis of symmetry is just gonna be x equals h, whatever h is, right? So in this case, x equals -1. And now what? Now we could make a t-table, and that works fine if we do that. So we've already got the point -1, -2, that's our vertex. Well, we could pick some other point on the t-table and use that. What would be a convenient one to plug in? I mean, I could plug in 0, that's fine to do, but if I plug in 0 for x, look what's gonna happen. If I plug 0 in, I'm gonna get 0 plus 1 squared, which is what? 0 plus 1 squared is 1, times -1/3 is not convenient, right? What if I plugged in, what's another one I could plug in? I could plug in, if I plug in 3, I'm gonna get 3 plus 1 is 4 squared is 16, that's still no good. I could plug in 2 though, couldn't I? I could plug in 2 because 2 plus 1 is 3, squared is 9, 9 times -1/3 is convenient, right? Now, any of those are gonna work, but it's just hard to graph a point that ends up with a fractional value, right? It's hard to know where it sits on the graph. So we could pick the point 2, and if I plug 2 in, what am I gonna get?
Plus 1 plus 3.
So let's find out. If I plug 2 into my function down here, f of something equals -1/3 times something plus 1 squared minus 2. Well, I'm plugging in a 2, so what's that give me? I'm going to get -1/3 times 3 squared minus 2. 3 squared is 9. So I get -1/3 times 9 minus 2. -1/3 times 9 is -3 minus 2 is what? So that's one way to do it. I could go 2 -5, right? That would work. I could do that. Or I could do it maybe an easier way, right? I could think about it in terms of my vertical dilation factor, -1/3, right? Now, normally, if we think about the shape of our parent graph parabola, if I go 1 to the right, I go up by 1. If I go 2 to the right, you already told me, I go up by 4. If I go 3 to the right, I'm going to go up by 9. So there's 3, 6, 9. Which of those heights would be convenient to multiply by A? The 9 would, wouldn't it? Right, so we could multiply 9 times -1/3 equals what? -3. So what that's telling us then is if I go over to the right by 3, instead of going up by 9, I'm going up by 9 times -1/3, which means I'm going up by -3. It's down to 3, right? And then from there, it's a piece of cake. Now all I have to do is just, I could reflect that point over, if I'm 3 to the right, I've got to be 3 to the left. And now I can just make the shape of this parabola like so, right? That make sense? Which way do you like? Let's take a vote. How many people vote for the t-table?
Tried and true.
Yeah, that's fine. How many people would prefer to stretch the parent graph? I would. I mean, you can do either one. You really can. You can do either one. But I feel like that's pretty easy to do, right? If you just pick, here's the shape of our parent graph. I can just take that parent graph and multiply a convenient height by A, and that's all I need to do, right? It's not a big deal. Okay, we good? All right, flip your desks around facing the back and you may work.